Why are roller coaster loops not circular? When thinking about roller coaster loops, you might think that they're perfectly circular. However, by looking closely at the Hydra from Dorney Park, for example, you can see that the loops are actually a teardrop shaped, known as a clothoid. But I'll get into that later. So first, let's look at why the loops aren't circular by seeing what would happen if they were circular. So here's a picture of a perfectly circular roller coaster loop. And the law of conservation of energy applies here to find the velocity of the cart. 1/2 mv squared equals mgh, and v squared equals 2gh. We know centripetal acceleration is v squared over r, so it also can be written as 2gh over r. If you look at this part in the loop here, the height of the cart is r, or the radius. If you plug this into the blue equation for acceleration to the right, this gives plus 2g's. At this point here, the height is 2 times the radius, and this gives plus 4g's when plugged into the blue equation to the right. When this is added to the force already experienced by the body by gravity, this results in a stress on the body of 6g's, and this is not good for the body. So how can we fix this? Thankfully, roller coasters are not built circular, and when we ride a roller coaster, the g-force is not 6g's, and there is not the rapid onset of acceleration that you would feel if the loop were a circle. This happens because the loops are clothoids, which is the teardrop shaped we saw earlier. A clothoid loop has a smaller radius of curvature at the top of the loop and a larger radius of curvature at the bottom of the loop. So let's examine the Talon roller coaster from Dorney Park. As the cart moved up the loop, its velocity decreased because its gravitational potential energy increased and kinetic energy decreased. When the cart traveled down the loop, its velocity increased because its kinetic energy increased and its gravitational potential energy decreased. As you can see, velocity and radius have a direct relationship here. This keeps the centripetal acceleration constant. Because of gravity, the rider will not experience a constant g-force, but the g-force is still a safe value, and to be exact, the Talon has a g-force of 4.5 g's.